Hi again. So we are trying to give some examples about the application operation amplifier usage. Up to now we have done inverting, non-inverting amplifiers. Now we're going to examine the summation circuit. Summation circuit. So let me write this name here. So we are saying this circuit does the summation process. How it does it? So we've got to analyze the circuit and say whether it does the summation or not. So summation means it's going to be, my output is going to be V out. These are the input voltages, so a coefficient VA, another coefficient VB, another coefficient VC. I made it a bit different and tried to find out these coefficients. I know that if these coefficients are equal to 1, so it's going to be direct summation. But if I can arrange these coefficients in any value, though that means I can multiply any input voltage with any number and to get the summation after this coefficient multiplication. So this analysis is not to analyze all the elements, current and voltages. It is the analysis of the output. That means our aim now is to find out the output voltage in terms of input voltages. These are independent sources voltages. So what is the definition relation of our operational amplifier? Just remind you, Vp minus Vn is almost 0. Ip is equal In is almost 0. So what does this mean? We said these are the node voltages. Between those two node voltages, the voltage we've got is equal to 0. So that voltage is 0. That 0 tells me that. So immediately we can say that since this is ground, so this 0 voltage, this difference is 0. So this point here, or this node here, our node voltage is equal to 0, isn't it? Because this is 0, this is 0, 0 comes here. So that node is short-circuited with the ground. So the node voltage is equal to 0. So we're going to write the Kirchhoff current law equation for this node. So the number of elements, 1, 2, 3, 4, 5 connections we've got to that node. So we're going to write 5 terms, but on the other hand, I know that since IN current is equal to 0, so I'm not going to write this current here because it is equal to 0. So I'm going to write addition of the 4 currents. So in order to write the Kirchhoff current law equation, we've got to choose the references for this one, for this one, for this one. So assume that this current is IA, and this IB, and this is IC. So IA are A resistors current, RB resistors current, and this is IC resistors current, and this current shows that reference IRF. So you could choose these as you like, but your result doesn't change. So you can choose these currents randomly, where your resulting equation is not going to change. So when you write this, so this current towards the node, so that's 1 minus IA, minus IB, minus IC, minus IRF. That means this current is equal to 0. This current towards the node, so that's why it is minus as well. The sign is minus. So this is not the equation that I am looking for. What I am looking for is this. So I'm going to transfer all these currents to these voltages. How I could do that? I could do it easily because this is that's ground, isn't it? So this current here, IA, is this node voltage. So that's the node voltage, VA minus VA over RA. So node voltage is VA minus 0 over RA. I didn't write minus 0. Let me write it here like that. But I'm not going to repeat it for the other ones because this is always 0. So it's going to be minus VB over RB minus VC over RC equal IRF. This current, what is this current? Let me clear. This current here, that's the node voltage VO, and that's ground VO minus 0 over RF. So VO minus over RF. It was left hand side, I move it to the right hand side, so the sign is positive. Okay, from that it's going to be V0 over RF is equal minus 1 over RA minus 1 over RB minus, so I should write this plus with RC VA, or let me write it other way around, so let me write it like that. VA VA VB VC. So if I write it now, V out equal minus RF over RA VA minus RF over RA. So you can put the minus parentheses. That is VA, that is VB, and that is VC, that is B. This is what I am looking for, isn't it? So what we can say, if the RF is equal RA is equal RB, if we choose this resistance value like this, so it's going to be V0 is minus VA plus VB plus VC. So this is the summation of these voltages. The output is the summation of the output. So this is what we are expecting, so that is this one. So when we do the calculation like that, we can say more than this, saying that we can arrange each input voltage coefficient as we like. By choosing the RF value, once you have chosen the RF value, then you can choose the RA value, this value that is, in order to get the coefficient the same as you expected for the VA, isn't it? Let's say RF is 100 and you want to connect coefficient 2, so you're going to choose the RA value to 50. 100 over 50 gives you 2, so the coefficient is 2. So you can arrange all the other inputs coefficients as you like by choosing these RA, RB, RC values. So that improves this summation operation. Before the digital computers, there were analog computers. In analog computers, this summation operation is done by using the operational amplifiers by these circuits. So that's the end of this video then. 1, 2, 3. So stop recording.